right, hello AP Chemistry students. So we're going to finish up our titration notes today where we left off. So last class we talked about the steps to take when we're dealing with the titration of a weak acid with a strong base. And so now we're actually going to plug in some numbers and see how we do the calculations. So here's an example of titrating weak acid, 0.1 molar acetic acid with strong base, sodium hydroxide. We're going to look at pH of this, just the acid alone, so the initial pH, and then after we've added 25, then 50, then 60 milliliters of 0.1 molar strong base sodium hydroxide. So the initial pH of the acid in the flask, and again, since it's a weak acid, it does not completely dissociate. We have the equation of the weak acid forming its conjugate base and hydrogen ion. So if we set up an ice table, we have 0.1 molar of our acid, and then we let the change in that, the dissociation of the acid, equal X. So, and since it's a weak acid and the Ka is so small, we can disregard the minus X. So plugging that into our equilibrium expression for the weak acid, we have Ka is equal to X squared over 0.1 equal to the equilibrium constant of 1.8 times 10 to the negative fifth. And just look that up on in the appendix for Kas. And that's the Ka for acetic acid. So when we solve for X, which is both the hydrogen ion concentration and the conjugate base acetate ion, we get a concentration of 1.34 times 10 to the negative third. And then taking the negative log of that, that will give us a pH of 2.87. So that represents our initial pH of just the acid in the flask. We did not have to convert that to moles because we weren't combining any substances together. So we could just go straight with our molarity like we were doing in chapter 16 with just straight up weak acids. Okay, now we're going to start doing the titration. And I just chose 25 milliliters of sodium hydroxide, and it is also 0.1 molar. So because now we are adding amounts together, we're adding 25 milliliters of hydroxide ion, we do have to convert to moles to add and subtract amounts and then convert it back to molarity, taking into account our total volume of the solution before we do any pH calculations. So setting up our ice table for the reaction that's going on now. So now as we add hydroxide ion, because sodium is just a spectator ion, so we don't care about that. As we add hydroxide ion to the mix, that is going to react with the weak acid and form water with the hydrogen ion of the weak acid, and then that will create the weak conjugate base acetate ion. So again, starting with our initial concentration of acetic acid, all I did is take the 0.1 molar acetic acid and multiply that by 0.05 liters to get the 0.005. So these are all moles. I didn't include the units, but this is moles. So that's just from the 0.1 molar times the 0.05 liters, and that gave us 0.005 moles of the acid in the flask. And then we are adding, oops, sorry, that's supposed to be a 0.002, my bad. That is, so we have 0.1 molar sodium hydroxide, and we are adding 0.025 liters, so that's supposed to be a 2, not a 4. So 0.0025 moles of sodium hydroxide. So all of the sodium hydroxide, the 0.0025 moles, is going to react with the acetic acid. So that's going to cause the concentration of the acetic acid to decrease by 0.0025. So when we subtract, that leaves us with 0.0025 moles of acetic acid, and the amount that reacted with the acetic acid is forming 0.0025 moles of acetate ion. Okay, so as this goes down by 0.0025, this goes up by 0.0025. And again, this is 0 because that's a typo. That's supposed to be 0.0025. So that's what's in our flask now. So there's no hydroxide ion. It got all used up to make water, and half of the original acid is now the conjugate base, the acetate ion. So since we have equal amounts of the acetate ion and its conjugate base, it's halfway to its equivalence point. So what we can do is any amount. I just chose 25, so it would be halfway to its equivalence point. But any amount we have leading up to its equivalence point, you can just plug it into the Henderson-Hasselbalch equation. The only difference is these two amounts won't be the same. We'll still do the same thing, subtract from the acid and add that amount to the conjugate base. But because they are equal with the Henderson-Hasselbalch equation, like we talked about the other day, we'll have the log of this over that, which equals 1, so the log of 1 is 0, so that means that the pH is equal to the pKa. So if we take the log of 1.8 times 10 to the negative fifth, the Ka for the acetic acid, that will give us the pKa, which is 4.74. So again, this will work using the Henderson-Hasselbalch equation for anything leading up to the equivalence point, regardless of what the amounts are. We just could skip the log of the conjugate base over the acid because they're both the same, and that causes our pH to equal the pKa. So you can see that the pH of the solution has gone up a little bit, but it's still an acidic solution, and it's still an acidic solution because we still have some of this weak acid in there. So it has gone up a little bit, but not, a lot, considering we did add 25 milliliters of strong base, but that's because we've created a buffer. And so we're forming acetate ion, and there's actually no hydroxide ion left over. So then I added a page because we ran out of room. So then the next volume is if we add a total. Now this is not 50 more milliliters, this is a total of 50 milliliters, so 25 more milliliters than what we already had before. So we add 50 milliliters. Oh, and one thing I forgot. Hold on, sorry, my bad. Let's go back. One thing I forgot is I kind of skipped a step since these are equivalent. Sorry, dog barking. Since these are equivalent, we didn't need to worry about converting them back to concentration because we were just going to use pH is equal to pKa. But if they weren't equal and we had to plug in their concentrations if they weren't equal and we had to plug in their concentrations to the Henderson-Hasselbalch, we would have had to take, these are in moles, we would have had to divide them by our total volume, which our total volume is 75 milliliters. So we would have to plug in, and I don't have my calculator on me right now, so I don't know. I can't tell you what that concentration would be, but we would have to convert it back to concentration by dividing by 0.075 liters. But again, since they're equal, we know that the log is going to be log 1, which is 0, so we don't have to worry about that. But any other amount, we would need to divide by their total volume to plug in to the log of the concentrations. Okay. Okay, so back onto here. So by adding 50 milliliters of base total, that gives us a total volume of 100 milliliters, 50 from the acid, 50 from the base. And so now, once we are at the equivalence point, again, we've created a buffer. This is what I'm dealing with, Boz. Be quiet. No, be quiet. Yeah, you're noisy. You're noisy. I'm trying to do notes. Somehow he always knows when I'm trying to need quiet. Okay, so what we have going on here, again, same equation as before. The hydroxide ion is reacting with the acid to form water and the conjugate base. He's almost done. There. Now he sat down, so he's quiet now. Okay, so again, we have our 0.005, again, I converted these to moles, 0.005 moles of acetate ion. And this time, because I've added 50 milliliters of base, I also have 0.005 moles of hydroxide ion. So all of the hydroxide ion is going to react with the acetic acid, and this time, because they're the same amount, there will no longer be any acetic acid left over. It will all form acetate ion. So as the hydroxide ion is reacting with the acetic acid, we are forming that much acetate ion. So after we've added 50 milliliters of base, we will have 0.005 moles of acetate ion, no acetic acid, no hydroxide ion. And again, we do need to convert that back over to molarity by dividing by our total volume. So we take the moles of acetate ion and divide it by the volume to get 0.05 molar acetate ion. Now, just like we saw before with the buffer, now we have hydrolysis occurring because we have acetate ion. So we have now a basic solution, and we have to use the Kb for acetate ion by taking the Kw and dividing it by acetic acid's Ka, the 1.8 times 10 to the negative fifth. So that gives us a Kb of 5.6 times 10 to the negative 10th. So this is now the reaction going on. We have acetate ion and water forming the acetic acid and hydroxide ion, which is what's giving us a basic solution when we have hydrolysis occurring. So here's our concentration of acetic acid, and then we have our X and X. So plugging it in with the Kb, not the Ka, the Kb. And again, as I said the other day, that was the common mistake people made on the quiz, is when hydrolysis was occurring, they forgot to convert over and use the appropriate equilibrium constant. So again, because of this hydroxide ion, we have to convert the Ka of acetic acid to Kb. So that gives us x squared over 0.05 is equal to 5.6 times 10 to the negative 10th. So solving for x, we get 5.3 times 10 to the negative 6, which is our hydroxide ion concentration. And then converting that to POH, that gives us 5.28. And then subtracting that from 14, that gives us a pH of 8.72. So that is our equivalence point. If you notice, that's higher than the equivalence point of a strong acid, strong base. So again, when we have a strong acid, strong base titration, our equivalence point is going to be 7 because we've created water and a neutral salt. But when we are titrating a strong base with a weak acid, we're going to have a pH that is above 7 because of this hydrolysis forming a basic solution. And that's always some type of question on the AP exam, is what pH would would a titration be with something like a weak acid, strong base? And it's always going to be somewhere above 7 because of this hydrolysis going on. And then once we get past that equivalence point, any extra sodium hydroxide beyond the 50 milliliters, so in this case 50 milliliters was our equivalence, our equal amount of base. So anything past 50 milliliters of base, all we're doing is adding extra hydroxide ion. So we determine our pH based on the surplus of hydroxide ion. In this case, with 60 milliliters of sodium hydroxide added, again that's 60 total, that means we have 10 extra milliliters of hydroxide ion floating around. Well, there's no acetic acid for that extra 10 milliliters of hydroxide ion to react with. So if we convert that to moles, so we have our 0.1 molar sodium hydroxide and 60 milliliters, that gives us 0.006 moles of hydroxide ion, but only 0.005 moles of it can react with the acid. And so that leaves us with 0.0010 moles of extra base floating around in the flask. And then converting that back to concentration, our total volume is 110 milliliters now. So we take that 0.001 moles of extra base that has nothing to react with and divide it by the total volume of 0.110, and that gives us a concentration of the additional base added of 0.00909, or we could have rounded up to 0.0091 molar. Now that's hydroxide ion, so when we take the log of that, that's going to give us a pOH of 2.04, and then converting that to pH is 11.96. So any volume past our equivalence point is just extra base floating around that has no acid to react with. So we just take that amount, divide it by the total volume to get the concentration of just the base alone, and determine the pOH and then the pH from it. So a little extra work with the strong acid, strong base. Again, if you can think through it in those phases of initially it's all acid, then leading up to the equivalence point, we subtract the base, and all of that base will react with acid, and we can use Henderson-Hasselbalch of the conjugate base divided by the conjugate acid. And then at the equivalence point, we have hydrolysis going on here, so we have to switch over to Kb. And then past the equivalence point is just excess base. Now the same is true for if we did it in the reverse. If we were titrating a weak base with a strong acid, everything would be the same. It would just be flip-flopped. So we'd be starting out with all weak base, and then leading up to the equivalence point, we would be reacting all of the acid with the weak base. So we could use the Henderson-Hasselbalch of taking the conjugate acid divided by the base. And then at the equivalence point, same thing, we have hydrolysis, only the hydrolysis of a weak base will form a conjugate acid. So we'll have an acidic solution at the equivalence point. And then anything past the equivalence point will have excess acid, which when we look at the titration curves, again, here's a strong acid being titrated with a strong base like we saw before. So we have a gradual change, and then right before the equivalence point, we have a steep slope with the equivalence pH of 7, and then another steep slope of all excess base, and this is what's going on. So here initially just the acids ions, and then here before the equivalence point in this region here, all the base is reacting with hydrogen ions. So you can see the hydrogen ion has decreased, and we have with the hydroxide, as it forms water with the hydrogen ion and hydroxide ion, and then we have the sodium spectator ion. And then at the equivalence point, we just have our salt and water. And then past the equivalence point, we still have our salt and water, and then we have excess hydroxide ion. And if we want to look at bases, we just flip-flop that. We'll talk more about that in a second. Here's the titration curve of a weak acid with a strong base. So again, initially, we just have the weak acid. And then as we add our strong base, again, the strong base reacts with some of the acid to form our conjugate base, and then here's our spectator ion. And then at the equivalence point, we have our conjugate base and our spectator ion. And then past the equivalence point, we have all this excess. Here's our sodium, here's our hydroxide ion. So we base our concentration on the excess hydroxide ion. So again, strong acid, strong base titration curve, weak acid, strong base. Now, the weaker the acid, the larger the pH and smaller the curve. So that's what this chart is showing you over here. The bottom, the black one, is showing you we have a strong acid, really steep curve as we titrate it with the strong base. And then with each of these curves, we have a weaker and weaker acid. So here's a weak acid. It's a little bit higher, lesser of a steep slope here. And you can see their equivalence points get higher and higher. So we're right at 7 on a strong acid, strong base. And then with each of the weak acids, the weaker and weaker acids, the larger the pH is at the equivalence point. And then again, we can flip everything around if we're going to put an acid in the burette and titrate a base. So we just swap out the titration curve. We're going to start up here with a high pH because we just have strong base only. And then as we add the strong acid, the equivalence point is still going to be at 7 because we'll still have a salt and water. And then past the equivalence point, we have excess hydrogen ion. So the curve will look the same, just in the opposite direction. And then titration of a weak base and strong acid is the same, but again, the equivalence point now will be less than 7. So if we were to kind of just flip this upside down, we would have the curve of titrating a weak base with the strong acid. So the equivalence points for those would all be less than 7. Don't really worry about titrations with polyprotic acids. Remember we talked about polyprotic acids in chapter 16, how each time they lose a hydrogen ion, the acid gets weaker and weaker, so its Ka gets smaller and smaller. This is what a titration curve would look like with a polyprotic acid. It could have 2 or 3 equivalence points. And as you can see, as we reach each equivalence point, we see a sharp raise in the pH. But again, you really don't need to worry about that. And then finally, we've used indicators before, but when we want to kind of get somewhat of an idea ahead of time of where our equivalence point is going to be, depending on what combination of acid and base we're titrating, so that we can pick an indicator that's going to fall in that range of where we're going to see the changeover from an acidic to a basic solution or vice versa. So like we've used phenolphthalein a lot when we're dealing with titrating a strong acid with a strong base, because it's going to change just after we get past a pH of 7. If we were going in the opposite direction and we were titrating a strong base with a strong acid, we would want something that would change color as we get just under a pH of 7. So maybe something like methyl red that's going to change color just after below a pH of 7. Oops, sorry. And so, again, don't worry about polyprotic acids. The big thing is the weak acid, strong base. That's the main thing to focus on. And I know Mr. Mager will love to help you if you have any questions. So go ahead and give your homework a try, and he'll be glad to help you if you're not sure of anything. So have a good day, and I will see you next class.